Okay, I will start. I hope the sound is fine and the screen is also visible. Can anyone confirm whether you can see the contents here? This is basically showing the second week. Okay, anyways, I will start. So, can you confirm whether I'm audible?
Yes, you're out.
Okay, I'm audible, right? Because I can't hear something. Let me just check the participants. Arjun Ajay. Arjun Ajay, can you hear me?
Yeah, you are audible. You are audible.
Okay, okay, thank you. And you have to just confirm that the screen is also visible because I can't see that.
Absolutely audible.
It's visible, right?
Yeah.
Okay, so you can see the week 1 and week 2 written here,
Okay.
right? So, yeah, because I will be starting for the week 2 session. So you can see that I mean it is written week 1 from 19th to 23rd January and week 2 from 26th to 30th January, right? Anyways, I will be starting. So, so I will be starting from the week 2. Let me just go to the second part. Okay. So can you see the simple energy balance model written here?
Yes.
Yes. Okay. So now in the first week we have looked into some basic concepts for the climate and mean state of the earth. Now we are slowly entering uh, into some more details for this particular subject. Now will obviously look into some simple energy balance model that would determine uh, the temperature of earth's surface and the top of the atmosphere, these two um, particular locations. This is a zero dimensional model because it doesn't have any information about latitude, longitude, the variation of latitude, longitude, and height. It is just, and also time. So it is just uh, determining the temperatures at two locations. One of the locations is the surface, and another location is at the top of the atmosphere. So, um, now irrespective of whatever the condition of the planet is, one thing is constant, that is solar constant. So though it has some variations, we assume it to be mostly constant. So the radiation that is reaching at the very first point, so before entering the atmosphere, that is constant. And what is the value for that? Anyone can volunteer? What is the value for the solar constant?
Yes.
Yes.
1360.
Yeah, so it is some 1300 some watts per meter square, what 1364 or something. But as Earth is a sphere, it only uh, receives one side of the radiation. So the sphere cannot completely get all the radiation, because only one part will get light, and that light also be tangential to some point and perpendicular to some other point. So these variations will be there. So now this solar constant, that is S by 4, will always be there. And now atmosphere or the surface, they start playing their own role. So the first point is the albedo, that is denoted by rho. Now rho is 0 0.3 for Earth. We have speculated from our observations by the satellites or different measurements. So what it will do is it will directly reflect some of the radiation. So the complete radiation of S by 4 will not enter into the planet. So that part will be reflected. So we first need to subtract that radiation with the complete one. That's why the 1 minus rho factor is there. So rho is subtracted from that particular value. Now, another assumption is made into further details, that is the absorptivity of the atmosphere, basically the solar absorptivity. So it is also contributing to some more um, absorption, that is preventing the complete radiation to reach the surface of the earth. Now that fraction is A, so it is further subtracted from that particular value. Now um, so the radiation that is reaching at the surface is S by 4 times 1 minus rho minus A. And another part is reaching the surface, that is due to the um, radiation from the top of the atmosphere. Now that we have assumed that the temperature is T subscript A at the top of the atmosphere. So according to Stefan's Boltzmann law, it is radiating sigma T A to the power 4. Now if there is some particular absorptivity for this radiation, which we denote as epsilon, that will the radiation will be modified by the factor of epsilon, and that radiation, due to the conservation of energy, will exactly be radiated from the surface of the earth, that is sigma Tg to the power 4. So that is the balance of the energy at the surface. Now balance at the top of the atmosphere is quite simple. So whatever is entering must go out. So S by 4 times 1 minus rho is entering, because we are considering the albedo. Now after that, the radiation going out is epsilon times sigma T A to the power 4, and another factor is 1 minus epsilon times sigma T G to the power 4. That is because the atmosphere is not a complete ideal black body with respect to the radiation that is emitted from the surface. It has some absorptivity. That's why this 1 minus epsilon factor is included. Now this is quite a simple model, because we can see the equations are quite simple, and we haven't used any complicated forms. So using some values for these parameters, we can get the observed mean temperature of the earth. So if we use these values, rho equals to 0.3, A equals to 0.2, epsilon equals to 0.95, and just perform some basic mathematics, we will get the temperature at surface is 288 Kelvin, and the temperature will be modified if you take different cases. For example, we can assume that the absorptivity is 0. That will give some value 303 Kelvin, which is higher than the observed value. Also we can assume the absorptivity from the atmosphere in the range of the wavelength that it is emitting from the surface is 1. So that is ideal black body type. So that will give you the surface temperature as 291.5 Kelvin. Now we can also assume that A equals to 0, but epsilon is 0 is equals to 0.95. That will give 299 Kelvin, and both are 0. So that is basically assuming no atmosphere. That will give the surface temperature as 255 Kelvin, because that is basically the emissive temperature of Earth. Okay. Now that is the picture. So the solar radiation S by 4 is coming due to albedo. The rho times S by 4 is reflected, so it is essentially giving S by 4 times 1 minus rho downward. Now absorption of the solar radiation by the atmosphere is there. So now at the surface it has the radiation of S by 4 times 1 minus rho minus a times S by 4 is the absorption by the atmosphere. Now, from the surface of the Earth, if it is maintaining temperature Tg, it will give the emission sigma Tg to the power 4, and from that 1 minus epsilon times sigma Tg to the power 4 will escape, and the atmosphere is at top of the atmosphere is at temperature Ta, so that will give the emission both ways because there are two surfaces, top and bottom. The top surface will emit the energy which is according to
So
status quo, while
emissivity
the
of surface is taken as one. Is it because it is taken as a black body? Is it?
huh? Yes.
No, the emissivity of the surface of the Earth is taken as one. Is it because it is a black body?
Yes, yes. Actually, for the surface, it is taken as one, right? So
Oh,
there we have not included that is sigma Tg to the power 4. So we have not included epsilon sigma Tg to the power 4, or you can say that epsilon is taken to be one.
okay.
That is the assumption. I mean, uh, that is also that might not be true also, but uh, at least for progressing, we have taken that assumption,
Thank you.
right? So someone wants to join this call. Okay. So okay, so far it is understandable, right?
Yes.
Now, um, so whatever this model is, I mean, there are different assumptions for the model. We have assumed the values of epsilon, a, sigma, and rho. Sigma is as a constant. So rho, a, and epsilon. It is giving the mean surface temperature accurately, 288 Kelvin, and also it is fitting with the observed temperature of Earth. So this is the simple energy balance model. However, there are heterogeneity in the surface of the Earth. At some places the temperature is warmer, at some places it is cooler, towards equator it is warmer, towards pole it is cooler, but as an average temperature it must follow the energy balance because local changes will of course happen, but totally the energy should be conserved. Otherwise, otherwise what will happen? I mean, if there is more energy entered into the earth, can you illustrate on that? What will happen?
Temperature will increase, right? The surface temperature.
Right. So the surface temperature will increase, and basically that is the cause for the global warming because whatever energy is now entered is not able to escape completely. So it is slowly increasing. The rate is slow, but it is increasing. Now, if it continues happening, then it will try to find some equilibrium state in which, in the new state, the energy entered and the energy exited would be exactly the same. Let me check for some comments. Someone said, sir, no voice. I'm audible, right?
Yeah, you're audible.
Okay, fine. Okay, so that is okay. Now, as we have this simple equation, uh, that is the surface temperature is related to different parameters. Now, using this simple equation, we can attribute to different changes for the surface temperature depending on different parameters. So what we will do is we will see some small changes in different parameters and try to see what are the effects of those. I will just give one or two examples, and rest of course professor has mentioned quite well in his lecture and you can try it out. So that is our basic formula, that sigma t g to the power 4 is equal to uh, this term, which is dependent on the albedo rho, the absorptivity A, the emissivity of the atmosphere epsilon in the particular basically the long wave radiation we call it. So we will take logarithm so of this. So log of both sides, it will give I mean, of course, just applying simple rules for the logarithm, we will get uh, this terms here, and we will differentiate uh, the both sides to get particular forms. So this term sigma tg to the power 4. So sigma is a constant, so the differential will be basically 0, but tg to the power 4, it will be 4 times d of tg divided by tg. You know this basic calculus, right? The,
Yes, yes.
right. Okay. So we are just differentiating. Now similarly, the second and the third terms are also being differentiated, and you will get the fractional form for the surface temperature relative to relative which is related to different parameters. The S is the solar constant, now rho is the albedo, A is the absorptivity, and from this equation you can calculate the changes in the surface temperature due to different factors. Okay. um, for example, if we change the solar constant, how will it affect the temperature? You can see that if all other terms are constant, so this part will vanish, this part will be equal to 0. Now dTg divided by Tg will be 1/4 of ds divided by s. Now let's say 1% increase in the solar radiation, that is 1 by 4% increase in the surface temperature. So which is essentially, if we want to get the total change, we just need to multiply Tg on both sides, so we will get the total change, that is 0.72 Kelvin increase. Similarly, if we increase, no, it is quite evident, like if there is more energy, then the temperature will increase. Now what is your speculation on albedo? If we increase the albedo, will the temperature increase or decrease? What are your thoughts on this?
If albedo increases, temperature will decrease, I think.
Right, so if albedo increases, it
More
means
is reflect,
more radiation is being
reflected.
reflected, so less radiation is entering into the atmosphere. That's why the due to less energy, the temperature would decrease. Now we will see the same. Just I will so if we increase the albedo by 2%, then the temperature will be decreased. I mean 0.25% decrease. That will be calculated as 0.72 Kelvin decrease in uh, the surface temperature. So 1% increase in solar radiation, in order to neutralize that effect, we need to increase 2% of the albedo. Now this albedo is a very um, let's say critical problem, because we cannot determine what would exactly happen. Now, albedo depends on cloud fraction, also the sea ice and the ocean fraction. I mean, the ice and the water, the distribution of these two, and different factors. So, let's say there is global warming, and due to that, of course, more water vapors will be there in the atmosphere, and there might be possibility of more cloud formation. Now, whether that cloud formation will increase the albedo or decrease the albedo is a matter of question. Now, it seems that if it increases albedo somehow, it will be beneficial for maintaining the temperature of Earth, but we are not sure, and this cloud albedo interaction is a matter of, I mean, important research. That's why it is debatable. Okay, so now this equation, I mean the form we have seen, that is valid for only the small changes in the parameters, like 1%, 2%, or let's say 4 5%. If there is large change in the parameters, then we have to start from this particular equation, and then see the changes considering the initial and the final state. Okay, because it is a differential equation, so you know the principle of um, derivative or differentiation. It works well in the small changes. Uh, you know about simple harmonic oscillations, right? In class 2 you have studied, might be. So in the simple harmonic oscillation, the oscillation should not be very high. It is recommended that the oscillation for a simple pendulum should be less than 4 degrees or so, in order to maintain the simple harmonic motion, because the simple assumptions of the derivative or the differential calculus will not work. So, okay. Now, now we will go to forcing and feedback part, and I would like to know your opinions about those things. Now, it is important to distinguish between forcing and feedback. So, forcing is externally applied, a change which is not considered to be a part of the internal system, or which is not happening due to internal processes. For example, we are mining coals, natural gas, and also this oils, petroleum, and we are burning those things. So that is increasing the carbon dioxide. So that is not a natural process. So that can be considered as a forcing. So the forcing by human interference is, I mean, this is a forcing. So the inclusion of the carbon dioxide by the human interference is a forcing. Now, feedback is the response of forcing via the internal mechanism that already exists on Earth. Uh, so yeah, we have given examples of forcing like deforestation, fossil fuel burning, like that. Now, solar change of solar constant is also another type of forcing, and if you follow the equation, you can see that it has quite a large impact on the surface temperature, because it almost changes 1 by 4% change in the surface temperature. So that is also important. Anyways, we will, as we will proceed in the course, we will see that there are implications of changes in the solar constant or the orientation of Earth, that is there, and due to that ice age also occurs. So we will discuss two feedbacks here, and I will ask you to provide your opinions about the other feedbacks. So first, positive feedback. Now, what is your basic understanding of the positive feedback? What do you understand by positive feedback? In a simple sentence, don't need to go to mathematics or so. Just a simple explanation you can give.
In radiative forcing will lead to increase in temperature. Yes,
Yes,
that
I
is
mean,
possible.
in case of temperature, it will increase. I mean, so
These
if you are giving me,
negative, if it is negative, then it will decrease.
right,
Negative feedback.
so basically you are perturbing the system in some way, and if you talk in general, so if you are changing, if you are dealing with a system, then changing some parameters of the system, that eventually leads to the change in the same direction for that particular parameter. That is positive feedback, right?
Okay. Yeah.
And if it is in the opposite direction, if you are increasing something, then eventually it is decreased, then it is negative feedback, right? So let's see some example in case of Earth. So for positive feedback, let's say we are not considering any other factors, just focus on this. So ice is melting, okay? Now if ice melts, so what will happen to the albedo?
Okay. Yes,
Albedo will decrease
definitely.
because, right, because I mean ice,
Water has
right, right.
less.
So ice is, so what is the basic color of ice? Is it is quite white, quite bright. So it reflects a lot of light, and water is very dark compared to ice. So it will absorb more. So the albedo will decrease, or it will lead to more absorption of solar light. and just define the reduced albedo like that. So more energy will be absorbed from the sun. Now if more energy is absorbed, the temperature will increase because more energy is absorbed, so it has to go somewhere. Now if the temperature increases, it will melt more ice, right? So you can find a loop here. Ice is melting, and melting of ice is causing melting of more ice, right? So if you start from here, you will end the loop here, but it is increasing the cause, I mean the origin of the cause. Or basically if ice forms, then it will form more ice, because just you take the negative of all the terms here, so you will see the opposite thing. If ice is forming more, then it will increase the albedo, so less energy will be absorbed and it will again form more ice. That's why it is positive feedback, as you mentioned. If it is having some particular um, direction, then eventually it is leading to the same direction, but in an intense way. That is the positive feedback. Same positive feedback can be given in another example in terms of temperatures. So temperature is increasing. Now, do you know what is permafrost? Have you heard of the term permafrost? Okay, so it is a thick layer of ice, mostly in the um, polar land regions. Let's say in Siberian region or Canada or different polar regions of Earth. There's a large deposit of ice, and that land is called permafrost. Now we believe that there is a large storage of methane gas below that. Now, if permafrost starts melting, then basically the pressure which is built due to ice will decrease because ice will melt. Now the pressure which is suppressed below that will be released, and you know that methane is a greenhouse gas, and methane is a very strong greenhouse gas. It is stronger than carbon dioxide, so small amount of methane can lead to large amount of absorption of the terrestrial radiation. So so what will it do? It will again increase the temperature, and it will again lead to the melting of the permafrost. So that will go on, that will keep going on. So that's why it is a positive feedback, right? So any doubt on that? If you have understood, you can say. Otherwise, for any question you can ask.
That's fine.
Okay, so we will now go to the negative feedback, if it is clear. Now for negative feedback, again we will give example from the temperature of earth. uh, Now, I mean, I first told that we are considering all other processes to be constant or not changing, because we are only focusing on these processes. Now for this we are now focusing on the temperature of earth. So if the temperature of earth increases, then the outgoing radiation will be more, because you know the Stephens Boltzmann law, we are always applying that. So sigma Tg to the power 4. So if temperature increases, then the outgoing radiation will also increase. Now if outgoing radiation is increasing, then of course it is exporting the energy outward to space. So it is a natural mechanism to decrease the temperature. It is a very fundamental mechanism that will always be there. That is the effect of the, it is also called Planck feedback. So if the temperature of earth increases, the temperature will drop. So it will, and also if the temperature of earth decreases, then the outgoing radiation will be also lower, and it will somehow try to increase the temperature. So that is example of negative feedback. Now one cause, so one forcing basically is causing the reduction of that particular forcing. So Here you can see increase of temperature, here you can see drop of temperature. So it will be somehow neutralized. So that is the negative feedback. Now, in order to get a stability, negative feedback is very important. If positive feedback is here, you will see that it will not stay at that particular equilibrium. If negative feedback is there, then due to the adjustment of the forces, it will try to be at that equilibrium point. Okay. Okay. Another example includes, but don't relate this that it is naturally removing carbon dioxide, because it is little sensitive. So carbon dioxide is increased, then of course due to the reaction of carbon dioxide with water, it will form more carbonic acid, and more carbonic acid will cause more chemical weathering. So basically the carbonate or other compounds of carbon will be formed, and that will basically act as a sink of carbon dioxide, and that will try to decrease in carbon dioxide. But yeah, I mean, we are critically increasing the carbon dioxide, I mean, we're highly increasing the carbon dioxide, so this mechanism actually is not efficient enough to protect us, or leading to the reduction of the carbon dioxide, because you can see that carbon dioxide is constantly increasing from the post-industrial point, and um, post-industrial revolution point, and these natural mechanisms are trying to suppress that, but it is not able to control it completely. Okay. Okay, so any queries on the negative feedback?
The lecture it was given that outgoing long-wave radiation reduces if carbon dioxide is increased. So how does that work actually? The lecture it was given.
Outgoing longer radiation is
Reduces if the carbon dioxide increases. That was what the lecture was.
in the
You
lecture.
in one of the lectures of the of
Okay, so he was relating to outgoing longer radiation with carbon dioxide, right?
yeah.
Okay, I think he has mentioned that if carbon dioxide is there, then it will act as an absorption element for the outgoing long wave radiation. So if you look at the absorption spectra of the carbon dioxide, it will absorb mostly near 10 micrometer band uh, of Earth's radiation. So basically the radiation will be trapped into the carbon dioxide band. So if there is a lot of carbon dioxide in the atmosphere, that will try to block the radiation that otherwise would have gone finally to the space.
Okay.
In that way, it is trying to block the radiation, but the effect will be that, because in order
Yes.
to reach one
Heat and
equilibrium point,
electricity.
the temperature has to increase, because it is blocking some of the radiation. So it will reach a state where the temperature of the earth will increase, and the new equilibrium point will be reached at that particular temperature. For example, in Venus, the carbon dioxide is very high, so it almost absorbs all of the radiation from the Venus that is releasing from the surface, and that slowly resulted in increase of the surface temperature, such that the incoming radiation and the outgoing radiation at that particular temperature are
Equal.
same. So it has to reach some equilibrium point, but that comes with a cost of increase of the temperature. Did you get the point?
Could you please explain one more time?
Yes. So if carbon dioxide is more in the atmosphere, then it will absorb more of the outgoing long wave radiation, because it is a property of carbon dioxide to absorb near the 10 micrometer, I think the
Yes.
Earth's radiation peaks at 10 micrometer band.
Yes.
So the outgoing long wave radiation that was earlier going to space, will now be decreased
decrease.
due to the carbon dioxide. I think that's what he wanted to mean,
Oh, okay, 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 okay.
right? But remember that that will come with a cost of increase in Earth's surface temperature because radiation is trapped and
Yeah.
heat conservation is always it is a very fundamental law.
Okay.
Okay, okay. Now these feedback systems can also be understood in other using other systems, not only the Earth. If you increase of something is eventually leading to decrease of that particular thing, then also it is a feedback mechanism. For example, um, just a hand waving argument, but we are going close to the fire, then at some point of time we will feel a lot of heat and we will be pushed back from the fire. So that is of course for our safety. But okay, now I would like to discuss about the following effect. Uh, what is your take on low clouds and high clouds in terms of feedback? So we will cover one by one. So what is the effect of low clouds on feedback? What is your opinion on that?
Low cloud would be at a low temperature,
Low clouds are at
a
a
higher temperature,
higher temperature.
higher temperature than high clouds.
High clouds are at a lower
So they
temperature.
will radiate. Low clouds will be high, so they will radiate more. Low clouds will radiate more
Yes, yes.
heat.
Low clouds will radiate more, but due to low clouds, the incoming solar radiation will also be reduced, right? You have seen uh, if there are low clouds in the atmosphere, then it blocks the sunlight,
Oh,
so
yeah,
it
yeah.
leads to cooling. Low clouds mainly leads to cooling,
Okay, okay.
and high clouds. If you see, these are also called. I mean, there are different names for clouds, cirrus clouds. So you will be able to see the sun from or moon, whatever it is, from that cloud, but it is at a very high point in the atmosphere, so the temperature is less, so the outgoing longer radiation from that cloud is also less. If outgoing radiation is less, then it is essentially leading to warming. So high
Yeah,
clouds lead to warming, low clouds lead to cooling.
yeah.
Now if a cloud is both, I mean it is stretching from all the way from the lower troposphere to the higher troposphere, it is very difficult to say what it will do because both the effects are there. Okay,
Okay.
so yeah, so basically low clouds and high clouds. But if it is given only low clouds or only high clouds, then you can conclude what their effects are. Okay. Now second point is the reduction in the lapse rate of the atmosphere. What do you think about that? What will it do? Do you know what is lapse rate?
The rate at which temperature decreases from surface to the top
Okay.
to
So
the troposphere.
yeah, because after in stratosphere the temperature again increases.
Yeah.
Anyways, let's consider the troposphere only. So what is the effect of the lapse rate on the temperature? So let's say the lapse rate is reduced. So what will it do?
If
If
lapse rate is reduced, then the temperature, the rate at which temperature decreases will, the slope will be less, right?
okay, so basically the temperature um, at the top of the troposphere
Be high.
will be relatively higher. Now it is if it is higher, then it will radiate more.
Yes.
If it is radiate more, then it will lead to some cooling of the
Cooling.
atmosphere.
Yes.
So decrease of the lapse rate will try to, or reduction of the lapse rate will try to cool the atmosphere. Similarly,
Yes.
increase of the lapse rate will try to increase the temperature of the lower troposphere or surface, whatever you think. Now, that is a crucial point. Feedback due to water vapor. What is the feedback of water vapor?
Positive.
Positive. Yes. Why?
Because increase. One second.
Because it absorbs the
Increase.
radiation in the same
Yeah, water
spectrum
vapor.
of the Earth.
Yeah, water vapor will absorb the radiation from the sun. What? No, the sea, the ocean water will. Is that right? I'm not sure.
Okay, so basically water absorbs, water vapor is a very strong greenhouse gas. Now, we don't consider it, but it is a very strong greenhouse gas, and it absorbs a lot of radiation which Earth emits as a outgoing long wave radiation. So, increase of the water vapor will trap those radiations, and that will eventually increase the temperature of the surface. Now, um, I think Professor showed one slide about the Manabe's experiment, in which he showed what is the effect of only increase in carbon dioxide and the effect of increase of carbon dioxide plus the water vapor. I think he had that slide. So carbon dioxide is not the only villain to cause the global warming. The water vapor is associated to that, but the water vapor is a result of the
Temperature.
increase in temperature, which is caused by the carbon dioxide increase. That is related to positive feedback. That's why the situation is more concerning than it would be if the effect was only due to carbon dioxide. So, yeah, as you mentioned, water vapor has a positive feedback effect on Earth's temperature. Now, surface albedo feedback, if albedo increases, then of course the temperature will decrease, right? Now, the last point, carbon dioxide and photosynthesis. So, okay. So, you just need to mention the relation between amount of carbon dioxide and photosynthesis. So, what is your take on this? If there are more carbon dioxide, what will happen? Due to on the plants only, not consider anything else. So, plants use carbon dioxide as raw material for their survival or for their growth. So, if there are more carbon dioxide molecules present in the atmosphere, it will help the photosynthesis, and that has some effect, negative effect, which will try to decrease the amount of carbon dioxide. So, of course, if carbon dioxide increases, then ideally the amount of plants and this uh, what I would say species which depend on the carbon dioxide will increase, and that will try to decrease the amount of carbon dioxide again. But it is not very useful, because still the carbon dioxide is steadily increasing and plants are unable to do so. Anyways, we are also causing deforestation. That is the problem. Okay. Okay, now I will discuss our assignment question, just some hints for the question, but I will cover one slide on the basics equations for the general circulation. Okay, what are the equations in which the models are run, and the models give outputs for different cases, different scenarios. We can control those models, but what equations they follow we must know. First comes the momentum balance equation. So you are familiar with Newton's second law,
Electricity engineer.
F equals to ma, right?
Yes.
So that is one particular form of the Newton's second law, but for fluids. Okay. Now that is the acceleration is related to gradient of p plus f. F is some external force, and gradient of p is the pressure gradient. I should include one rho here. That should be gradient of p divided by rho, but okay. This denote the equations of motion for the three directions. So this one denotes acceleration, and this one denotes the forces. Okay. So in x, y, z directions, because we have three coordinates x, y, z, this will give us three equations for motion. Now most of the cases, the vertical vertical direction, the hydrostatic balance is assumed. So there is no motion in the z direction or in the vertical direction, because it assumes that they are vertically stable. Now this description will not work when there is strong convection. Suppose a very big cloud is forming or a tornado has formed, then these descriptions will not work. But on an average, the vertical assumption, that is the hydrostatic balance, will work fine. uh, Now the second equation is the conservation of mass, um, which is uh, basically considering one particular box, and whatever is entering is also exiting through the box. That is the continuity equation. So that is the change of material in the box will be proportional to the amount which is entering. Now this is the divergence operator operating on the mass, or the density flux of into the box. You are familiar with the vector calculus?
Yeah.
Okay, so basically this is the local change of that particular variable rho, and this is the divergence operator on the flux, and rho times v is the flux. So these two will be cancelling each other, and that is the conservation of mass essentially. Now similarly, conservation of energy is there, that we know from our school studies. So that is the form of the conservation of energy. Here Cp is the specific heat at constant pressure, T is the temperature. So d capital T divided by d small t denotes the rate of change of temperature, and this is the pressure, rate of change of pressure, and this is the heat applied, or the source or sink of heat, you can see, think like that. The first law of the thermodynamics. Now we also assume ideal gas for the atmosphere. uh, Mostly it works. And also we can see the evaporation, precipitation in the atmosphere, these are essential parts. So there are equations for moisture also, for example moisture conservation equation. And in ocean, the salinity, along with the temperature, the salinity is important, because uh, you know about the process of diffusion or advection diffusion, you know about those processes. These processes become important in the ocean, so we also need to uh, consider the salinity in the ocean. So these laws are basically implanted in the system or the models to get the outputs. Okay, so okay, let's go to the stable and unstable equilibrium, then I will discuss the problems. Okay, now first, unstable equilibrium, just given the definition. A perturbation, if the feedback is in the same direction of the perturbation, then the perturbation of course will be increased, enhanced. So the system will not return to its equilibrium state. So um, suppose you are placing a ball on a top of a hill. Okay, so the hill is like this one. So the top of a hill, you are putting one ball. So if you give some small perturbation to the ball, what will happen to the ball?
Will go downwards if it is on the top.
It will keep going down, because small perturbation means small, it is converting potential energy to kinetic energy, and if the slope is there, it will again have more chance to convert the potential energy to kinetic energy, so it will keep on going down. Now think of the similar situation, but you put the ball in a valley, not in a hill, in a valley. If you are putting one ball, what will happen if you just give some small perturbation to the ball?
It will be stable. It will remain
So,
at that
yes,
position,
because
somewhere near that position, oscillate around some position.
yes, of
That
course. Because if it starts going somewhere else, its potential energy will be increased, and that will try to basically push the ball back into that initial position. So these are basically stable and unstable equilibrium points. Similarly, the perturbations are, these are basically, this is the same description for the stable and the unstable equilibrium points. So other rest is the mathematics, but that is the basic concept. Now, for mathematics, let's consider the equation uh, that derivative of x is x times 1 minus x square. Now, I would ask you for the equilibrium point, it will have no change. So, dx dt will be equal
Zero,
to 0. So, what are the solutions for dx dt equals to 0?
0, 1, minus 1.
0 plus minus 1. Yeah. So, that is these are the
That's right.
solutions. Now, we need to identify whether they are stable or unstable. Now, for stable, suppose you are giving some small perturbation to close to the equilibrium point. If the perturbation has the same sign as the dx dt, it will be unstable. It has, if it has the opposite sign, then it will be stable. Okay, let's consider the first the point 0, x equals to 0. Now we are giving some small perturbation. Let's say we place x into some point, let's say at 0.1. Then just consider that value. Dx dt will be 0.1 times 1 minus uh, 0.1 square of that. So let's say x is 0.1, then dx dt will be 0.1 times 1 minus 0.1 square, which is a positive number. So that is basically 1 minus 0.01, but which is positive. So putting x into 0.1 will push x away from x equals to 0. Similarly, if you put x equals to minus 0.1, it will be minus 0.1 times 1 minus 0.01, that is a negative number. So putting x, a negative value of x will push x further into the negative direction. That's why x equals to 0 is an unstable point, equilibrium point. Now, if you apply the same logic at the point x equals to minus 1 and x equals to plus 1, you will find that if you put the values for x greater than 1, it will have negative values. Suppose if you put x equals to 1.1, then it will be positive, but that part will be negative because it will be something close to 1 minus 1.21, like that. It will be negative. So it will try to uh, return to x equals to 1. Similarly, if you put x equals to minus 1 and consider some points left to that, right to that, anywhere, it will try to return to that x equals to minus 1 point. So both x equals to 1 and x equals to minus 1 points are stable equilibrium, and x equals to 0 is an unstable point. Similarly, the similar logic can be applied for Earth system. For Earth, C is the heat capacity, let's say, and this is a temperature change. So that will be equal to the total radiation, that is incoming minus outgoing radiation. Now, if due to some reason, if the temperature increases and the radiation is also having a positive value, then it will be an unstable point. If the temperature increases, then the radiation has, if it has a negative value, then it will try to push the temperature to its initial position. So it will be a stable equilibrium point. Now the biggest question is, now the way we are increasing the temperature of earth by emitting a lot of greenhouse gases, will it lead to stable or unstable equilibrium point? If you cross one certain point when there is no return back, then we will be into trouble, because the system will then naturally go to its unstable point, and maybe it will lead to a point where the temperature will be increasing constantly, as we have seen has happened in Venus. So that is a very big concern for all of the flora and fauna of the earth. So any question on this? Yeah, it was a little mathematical example, so I will be happy to answer any queries or questions on this point.
So in the example, between minus 1 to 1, it is stable, is it?
See, this
Sorry.
this is the graph.
Oh, okay.
So there are 3 points. One
So,
is x equals to 0, another is x equals to 1, and the third point is x equals to minus 1. So these 3 points are equilibrium, because dx dt is equal to 0 at these 3 points. Now x equals to 0 is an unstable point, x equals to 1 and minus 1 are stable points, because if you give some small value, let's see, if you give some, the graph will say everything. If you give some small value here, you see dx dt will be positive, so it will try to
Mm.
increase the value more until it reaches dx dt equals to 0. So if it is above that dotted line, then it will be having positive values, it will increase. If it has values negative, then it will decrease. So if you put the point here, it will have the negative value and it will push it back. The arrows are denoting the sign of pushing. Similar logic applies for x equals to minus 1. If you have negative values here, then it will have positive push or positive value of dx dt, that will push the system back to that x equals to minus 1 point. And if you are having some positive, I mean higher values compared to x equals to minus 1, then it will have negative value of dx dt, that will again
Push
try
it
this
down.
try to make the system back to minus x equals to minus 1.
Okay.
Any queries about that? Did you understand it, or I will explain some in some more details?
Could you explain it in more detail?
Okay, so just no, I will just ask you what point. Just you just pick one point, then I will start explaining from that point. So what point you would like to first address?
Minus point 0.5 or point 0.5.
Okay, so let's consider the point x equals to minus 0.5. Okay,
Okay.
now at that point, let's say this point is here. The arrows of course are denoting that it will push the system to x equals to minus 1, but let's do it in the calculation. What would the value of dx dt be? X equals to minus 0.5, so it will be minus 0.5 times 1 minus, I think, 0.02,
Negative.
0.25,
Mm,
right?
yeah, point
So
0.
so
Point
it is
0.5
negative.
into negative.
Now negative means it will decrease the value of x. So if you put a point x equals to minus 0.5, it will decrease the value of x until what point? Until the point where it becomes dx dt equals to 0. Because at x equals to minus 1, it will not decrease more again, because it will reach the equilibrium point, it will not decrease. So are you clear about the logic? X equals to 0 minus 0.5.
Yes.
Now, if you put the point at x equals to 0.5, the value of x dx dt will be 0.5 times 1 minus 0.25, which is a positive value, right?
Yes.
So it will push the system towards higher values, because dx dt is positive at x equals to 0.5. Until what point? Until the point where dx dt is equal to 0. It cannot cross the
Yes.
boundary, because it will be 0 at that point. So it will reach that value because it is a stable equilibrium point, or just because it is reaching that and not going anywhere else, it is a stable equilibrium. In the same logic, x equals to minus 1 is a stable equilibrium point. At x equals to 0,
Will
it
it
is a
oscillate? That is what at one at x is equal to 1, because downward it will go, then or it will be, there will be a negative gradient, and upward it will go, there will be uh,
right. Yes, yes. I mean, yeah. I mean, if you think in terms of oscillations, if you consider it as a potential, then the oscillations will be there. So if it maintains some value at x equals to 1, then it will oscillate. But if you just put it somewhere else, it will eventually reach the value at x equals to plus 1. So it will oscillate, but it will oscillate centered around x equals to 1. And if the system has frictional effects, then the oscillations will die down and it will be stable at x equals to 1. Similar case for x equals to minus 1. But if you put it in x equals to 0, it will not stay there. I mean, if
Yes.
you give some small perturbation, it will not stay there. It will either reach x equals to plus 1 or reach x equals to
According to
minus 1, depending on the direction of the perturbation.
okay.
Similarly, I think in case of Earth, there was three situation. One is snowball Earth, another is ice age Earth, and the third one is the present day climate, right? So, um for the snowball Earth and present day climate both are considered to be stable, because if the temperature is increased or decreased a bit, it will again reach to that point. But ice age is unstable because the ice albedo feedback is feedback such that it eventually leads to one of the snowball Earth, or I would say present day climate, which is mostly snow free Earth in that sense. So you can relate this concept to the system of Earth. Instead of dx dt, you just need to consider c times d temperature dt, but you need to identify the radiation parameters correctly. That is the crucial part of this energy balance. Otherwise, you won't be able to get anything properly. So that is the point where people are struggling. Researchers are struggling. Okay, so anything else for this equilibrium points? If not, I will go to the simpler version of our problems that are given in this week. Okay, so I will proceed to the simpler version of the problems, because I cannot just solve the problems. So one problem was about a hypothetical planet which is called Daisy World, which consists of white and black daisies. The concept is that if there is reduction in temperature, or the temperature is decreased, then the black daisies will increase in number, and that will absorb more radiation. So it will eventually decrease the reflection, or the albedo, that will increase the temperature. And if the temperature is increased, then the white daisies will be bloomed. So it will increase the albedo, decrease the absorption, and that will lead to a decrease in the temperature. So the planet will try to maintain some equilibrium temperature. Now in this problem, we have said the equilibrium temperature is, let's say, T, for and the planet is full of daisies, nothing else is there. In our problem, there are also bare land, but let's say in this problem there is 50% black and 50% white daisies on the surface. Now let's say solar radiation decreases by 10%, but the temperatures are the temperature remains the same. So what is the modified fraction of white and black daisies? Here we have also changed the relative albedo of the white and the black daisies. It is 0.1 for black daisy and 0.9 for white daisies. So okay, so with the question, I would like to know your approach on this problem. Not every mathematical steps, but the approach. What would you like to do first? Anyone? I think Arun Ajay is there. So therefore, okay. So I would like to ask someone else, because Arun Ajay is reporting the law. So Bintu, Droma, are you there? Bintu Droma is not there. Uh, so Vaishnavi, are you there? Okay, seems that is also not there. Okay, so Arun, you can just share your approach on this problem.
We show the problem. Right. So first we have to, I think we have to calculate the effective albedo for the for H0 into H0 by 4 into 1 minus alpha. From that you will get the temperature, which is equal to the equilibrium temperature sigma T raised to 4.
Right,
Then during the next step we have to decrease the, so it will be zero point 0.9 into S
right.
into,
It will decrease. Right,
okay, area fraction will be 1 if it is A1 is equal to, suppose, okay, area fraction of 1 will be the 1 minus, if it is A1 for white daisies, then the black daisies, then it will be 1 minus A1.
okay,
So
so
it,
you
I
have to
think it is
assume. Right.
area fraction. So I think
So you have to basically find the area fraction such that it satisfies the same equilibrium temperature.
so
Right.
yeah, so it's equal to sigma, same as the equilibrium temperature.
Right. So, and what is your basic concept about the case where the temperature, basically the solar radiation decreases? So the area fraction of white daisy will increase or decrease, or what happened to the black daisy? What is your guess on that? Considering the value of the albedos, 0.1, 0.9, like that.
From the equation, I think that as solar radiation decreases,
Hmm.
uh, albedo should increase. White daisies, because it is 1 minus alpha. So if alpha increases, then
See, now there is a biological effect
we have
associated
to
with
maintain. Okay, we have to maintain the equation. So
right.
if it is, if solar radiation decreases by 10 percentage, the albedo should also uh,
Decrease,
decrease.
right?
Decrease, right?
So if the solar radiation decreases, then in order to maintain the same energy entering into the atmosphere, or the planet, we have to increase the absorption of the solar radiation. That is,
Albedo will decrease.
so albedo will decrease, right? Now albedo can decrease by what process? If black daisies are there, if white daisies are there, it will
Like black
reflect more.
daisies should be more because it has more or less.
Yeah, so
The,
black daisies absorb more. So we need to increase the population of black daisies in that case. Similarly, if there is increase of solar radiation by 10% or whatever fraction, we need to increase the
increase.
number of white daisies because it will reflect more, such that the radiation entered into the atmosphere of that daisy planet will be constant. That we need to do. So that is the general approach. Basic, without going into the equation, we can say that. Now, what would the exact fraction be is left on the calculation. So sigma t to the power 4, that is equal to the solar constant by 4 times, there is the area fraction is 0.5 for the black and white daisies, and the absorptivity are also 0.9 and 0.1 for these two species. So we eventually get that it is s by 4 times 0.5. Now it is the radiation basically entering into the planet to maintain the equilibrium temperature of T. Now sigma is a constant, right? So if T is a constant, the sigma T to the power 4 is basically a constant, because we have said that the temperature is maintained, the same temperature is maintained. So S is actually uh, now be varying. So if S is varying, then the factor which is multiplying with S should also vary in order to make the product of these two constant. Now following that, we are going into the calculation part. Now we have assumed that R is the fraction of white daisies. So 1 minus R, as you said, will be the fraction of black daisies. So we will equate that. So sigma t to the power 4, which is essentially s by 4 times 0.5, will be equal to 0.1 times R plus 0.9 times 1 minus R, because it is the um, absorption uh, for the white daisies, and 0.9 is the absorption for the black daisies. Now that is after doing the mathematics, we get the results that R is 31 by 72. So the fraction of white daisies, it is less than 0.5, okay, because the half of 72 is 36, so it is 31 is less than 36. So the fraction of white daisies has decreased as expected. Okay, so the white daisies are replaced by black daisies. Now similarly, if we increase the solar radiation by 10%, so the planet should I mean become hotter if there were no changes, but then the daisies will become active, and white daisies basically will become active, and that will replace the black daisies. So instead of 0.9, we have now used 1.1 in that equation, and we have again assumed the fraction of white daisies to be R. So after the calculation, it gives us R equals to 49 by 88, which is greater than 0.5, because the half of 88 is 44 and 49 is greater than 44. So you can see that the white daisies have increased, and due to the increase of the white daisies, the excess solar radiation is somehow balanced, so it is able to reflect more, so absorb less, to maintain the same amount of energy into entering into the planet. Okay, any doubts on this?
It's clear.
Okay, okay. Now in our system, earth system also, there are different feedback mechanisms which control uh, the temperature of earth. Now due to some reasons, the temperature is now not being controlled, mainly due to the forcing of CO2. So it is slowly increasing throughout the last 150 years. Okay. Okay. Now there was another question on feedback. While there would be different notations for feedback and the mathematical calculation of this, suppose there is some notation which professor gave on his lectures. In the assignments, I saw some other notations are there, but your basic concepts should be clear, such that you are able to answer the problem and get the feeling of it, how one is affecting the result or the output, or what is the basic mechanism for the feedback. So just keep in mind that, I mean, you shouldn't blindly follow uh, any particular uh, notation, but should be flexible to all the notations with respect to the concept. If the concept is fine, then any notation will work. Okay, so here we have defined forcing on the system, delta F. So if some forcing is applied, then there would be direct effect of that, and the direct response would be delta T0 is 1 by lambda 0 delta F. That is according to our definition. Okay. Now, if there were no feedbacks, then what would happen is that the temperature would have stopped after the increment of delta T0. But there are feedback mechanisms in the system. So the feedback mechanisms will start working once the temperature has increased by delta T0 amount. Now that will again change the forcing, or basically the effective forcing, and that will again change the temperature, and this will go on. Now if you think from this approach, then it will seem like an infinite series, and it will never give you exact answer, or we need to do recursive steps to get that. So we will attack the problem from the final state, so as that we assume that the system will eventually reach a steady state where the final temperature response is delta T. That is the direct temperature response delta T0, and the final temperature response is delta T. And there are feedback mechanisms in the system which is feeding back. Basically, if there is some temperature change, it is feeding back the temperature using the factors lambda 1, lambda 2 times like that, lambda n. So let's say there are n such feedback factors. So I think here we have used n different feedback factors. That is just for illustration. Now in the balance system, the delta F was the forcing, and the delta F I have subscripted FB for feedback. That is the forcing plus feedback in the system. So that will have the connection with the direct response. So that will be multiplied with the factor of 1 by lambda 0, and that will give us the final temperature increment delta T. So that is the forcing plus feedback, which will reflect the change, uh, 1 by lambda 0 times that, which will be the final response delta T. So is that step clear? If that is clear, then the rest will be just mathematics. So is that first step is clear?
Yes.
Okay. If that is clear, then we will just input the value of delta FB. What is that? So delta FB is the feedback which is feeding back from the delta T with different parameters lambda 1, lambda 2 like that. So lambda 1 times delta T, lambda 2 times delta T up to, uh, if there are n factors, it will be summation over lambda 1 to lambda n times delta T. Now we will just insert this value, and we will get that, um, delta F is, we will take the lambda 0 to the other side, and delta F will be delta T times lambda 0 minus summation over I equals to 1 to n lambda I. Okay. So such that we will get the value delta T equals to, delta F divided by lambda 0 minus lambda 1 minus lambda 2 lambda 3 like that. And we have just divided lambda on the both sides because we have that particular direct response delta T0. So we are getting the value of delta T equals to delta T0 divided by 1
Your
plus.
voice, the speed is coming as quick,
Huh?
very fast. The speed of which you are telling is coming very fast.
The
We can,
speed is coming very fast.
yeah.
Okay. I'll slow down, right? But the voice is clear, right?
Your voice is clear, but
Okay. I will slow down. I think I spoke a little fast. Okay. I will. So let's come to this point. Delta FB. It is the feedback effect. What is the feedback? Feedback is if there is a response delta T, some fraction of that will again enter into the system
mm, yeah,
with
okay.
coefficients lambda 1, lambda 2, lambda 3 like that. So the final input of the system will be delta F plus delta T times this feedbacks, which is, uh, here just use the summation notation I equals to 1 to n lambda I
Okay,
times
okay.
delta T. Okay. Now in that
Yeah.
we will get the delta f plus delta fb, and that is the let's say input, and the output will be direct response to that input, which is that divided by lambda 0. That will give us the final output delta t, because that is the state after reaching the equilibrium. Now
Okay.
we will express delta fb here in terms of lambda 1 lambda 2, and the equation we will take lambda to the other side. So delta f will be lambda 0 times delta t minus delta fb. So we will write delta fb in terms of this uh, lambda I delta t, and from there we will get the equation delta t is equal to delta t0 divided by 1 minus f. For getting delta t0, we have just used the initial equation, the direct forcing equation.
Delta F by lambda. Okay.
Now this factor 1 minus f, that is 1 by 1 minus f, is actually defined as gain. So now the f equals to summation over I equals to 1 to n lambda divided by lambda 0 is the feedback parameter. Okay. Now
Okay.
please note that you are getting some direct response without feedback. Now if the feedback is there, it will change the direct response. Now if f is equal to 0, then delta t is equal to delta 0. So if there
And
is
there won't
no
be any.
so if delta t is equal to delta t0, then there is no feedback. It also aligns with the our notation that f is equal to 0. But if f is between 0 to 1, then 1 minus f will be uh,
Less than.
between 0
Mm,
to 1, less than 1. If it is less than 1, then delta t will be greater than delta 0, delta
increase.
t0, because you are dividing it something by less than 1. So it
Yeah.
will be a positive feedback.
Positively.
If f is positive, then delta t will be greater than delta t0. So your final effect is basically amplified by the initial effect, initial forcing. That's why it is
Yes.
called positive feedback. Similarly, if f is negative due to some reason, then 1 minus f will be greater than 1. Then 1 by 1 minus f will be less than 1, because we are dividing it by 1. So delta t will be less than delta t0, right? So the final
Yes.
increase in temperature will be less than that which would have happened due to the direct response. That is negative feedback. So that is the difference between positive and negative feedback in terms of mathematics. Is this clear?
Yeah.
Okay.
Yes.
Now in your assignment, you might have given minus 1 by lambda 0, minus 1 by lambda 1, minus 1 by lambda 2, but the mathematics is basically the same. In the assignment, whatever notations is used, I think the questions are very straightforward, so just follow their notation and do the mathematics. But the concepts you should keep in mind. Okay.
I think it's just substituting in the formula, right? I think the formula.
I mean, the assignment there is just formula, some formula given. You have to just follow the formula.
Okay.
I'm just telling that the basic um, concept or
Okay.
basic impression of feedback, this thing should remain irrespective of the notations used. And 1 by 1 minus is f is often called the gain, because it is the final output with respect to the initial input. Okay. Okay, I think just for a completion, I will go through a problem here now. Okay, so okay, I will interact with. Let me just check once if someone else is there. Otherwise, I will ask you. I mean, Arun. But are you here, Mintu Drama Megaji? Mintu Drama Megaji? Okay, not here. Vaishnavi, you are here. Okay, she's also not here. So I will go to the problem. Now I will just explain it, and Arjun, you can just coordinate.
Right.
So the problem is that the direct feedback parameter is given as lambda 0 equals to 2. Forget about the units, but for convenience we have just given watt per meter square per Kelvin. And the other two feedbacks are lambda 1, lambda 2 minus 1.5 minus and 2.5 watt per meter square per Kelvin. Now the forcing given is 3 watt per meter square. Now following the equation, just tell us uh, what would the direct response would be. So direct response is
1
delta
by
F by lambda 0.
and yeah, 1 by yeah, 3 by
So that is
3 by 2,
basically 3 by 2 Kelvin. So if there is forcing of 3 watts per meter square, if there is no other feedback, so
will
lambda 1 and lambda 2 both are equal to 0, then the response you will get is 1.5 Kelvin increase or decrease depending on the direction in the temperature. Okay.
yes.
Okay. So that is there. So you can see that. Now, now consider all the feedback mechanisms and tell what would happen if all the feedbacks are there.
According to the formula, we have to sum it from sigma lambda I
Right,
according to that
right,
formula, right?
right. So basically, in order to get the delta t, you need to just sum lambda 0 minus lambda 1 like that. You need to use this formula. So lambda 0 minus lambda 1 up to lambda I, and then divide on the other side, so you will get the formula. So yeah, so we have just used lambda 0 minus lambda 1 minus lambda 2 here. So we have inserted the particular values, and 3 divided by that, yeah, that gives 3 Kelvin. Mathematics is fine. Okay, so you can see that there is an effect of the feedback on the final temperature. Now you can see that the first one is here, one negative feedback, the second one is one positive feedback, and together they are giving uh,
First.
the positive feedback,
Okay.
because if the value of f is 0.5, right? So you can calculate value of f also. As f is positive, we can expect the feedback
Okay.
to be positive, and you can see that the final temperature increases 3 Kelvin with respect to the initial temperature increase of 1.5 Kelvin. So this is different from the initial, and it has increased from the initial value. Now let's say if I have if I had altered the values, let's say minus 1.5 and minus 2.5, then the scenario would be different. So then it would be 4, together it would be
Right.
4 watts per meter square, then 2 minus 4, it will have some negative values of the feedback. So it will also lead to decrease in the temperature. So it will have how much, 2 plus 4,
Negative.
that is 6.
Minus
So
1 point.
0.5 Kelvin, something like that. So
Okay.
it will be negative. Now here it is overall positive, so the system is warmed more than the direct response. Now what happens in our weather is the carbon dioxide forcing has some direct response, but the water vapor has some more positive feedback, so it amplifies the effect of carbon dioxide. What happens is, as we discussed in the feedback due to water vapor, so you also mentioned that it is positive. So feedback due to water vapor is positive. Now due to carbon dioxide, the temperature increases. If the temperature increases, you know about Clausius Clapeyron equation.
I think it's phase change is related to phase changes of gases, right?
Yes,
What
exactly.
what
It is actually related to phase change of any item, any system in the thermodynamics. But here, in context of weather and
water.
climate, we relate to the water phase change. So water evaporates into vapor, and what is the amount of water that will be there. So 1 degree Celsius or 1 Kelvin increase results in the 7% increase in the humidity, like that. So so due to temperature increase that is initially started by the increase of carbon dioxide, the water vapor becomes higher in amount in the atmosphere. Now water vapor is a very strong greenhouse gas basically. So if water vapor is there, it will trap more radiation. So it will act like an assistant of carbon dioxide to increase the temperature of earth. It will trap the radiation more. It will give us a positive feedback. So whatever temperature would have been increased due to carbon dioxide is further increased due to the water vapor. That is one positive feedback. So there comes the necessity of the feedback analysis. Now in earth it is a complex system. Involves a lot of feedback factors. So I mean, these are just a few of them. Now researchers are still looking at those processes, and what would the exact temperature be depends on those feedback factors, and that's how the climate models are run. That's how the outputs are interpreted and the results are documented. So that is that's why this all the concepts regarding feedback, forcing, or equilibrium points are important to this uh, subject. Okay, so yeah, any queries on? I think I have this much today, but any queries? If you have any queries, you can ask.
Moisture conservation of the
What?
atmosphere, the moisture conservation equation, not
Right.
equation, in you said about the five types of equation. One of them you mentioned moisture conservation.
Ah.
Could you just explain what it is?
Okay, okay, okay.
Ah,
Uh,
this one, equation.
yeah. So for moisture and salinity, what happens is um, they are related to different processes. As you mentioned, for the phase change, if moisture has some phase change, it will incur in the heating or cooling of the atmosphere. If moisture is condensed, it will result in heating of the atmosphere because it releases the latent heat, right? If it becomes water, I mean, if moisture forms clouds, then it releases latent heat in the atmosphere. Now the latent heat will somehow enter the conservation of energy equation, and that will somehow be related to the momentum equation, dynamics equation, because that is again related to the conservation of mass, this equation. So moisture equation
Mhm.
consists of the conservation of moisture, the source of, so the change of moisture is basically related to the advection of moisture and the source and sinks of moisture. If let's say you are assuming, shall I open the paint here? Let's try this brush. Okay, so let's say you are assuming a control volume here.
Okay,
Now in that control volume, so there is influx of moisture and also outflux of moisture. I will,
okay.
let's say M denotes the moisture. Don't be confused. M is not mass. So M incoming, M outgoing. Now there are processes like evaporation, which will act as a source of moisture because the water from the ground is, let's denote it as E.
Like drop latent heat and
Yes,
so
so it,
that
it will have some latent heating because it will change the phase from the water to the vapor.
water vapor.
And similarly precipitation, if precipitation is there, then the clouds will be formed, so it will release some latent heat. Now the latent heat will enter the heat equation. Now the heat equation will enter the conservation of mass equation because it is related to the density of the atmosphere. Now the conservation of mass is related to the velocity, so it will enter the velocity equation or the momentum equation. So we need another additional equation for the moisture. for atmosphere.
Okay.
Also there is diffusion of moisture that sometimes can be considered in the atmosphere. If there is more, diffusion means flow of moisture from higher concentration to lower concentration. If there at one place there is
So
huh?
this is basically conservation of mass for moisture, like
It is
because
conservation of mass for moisture, right? But the additional process is also the conservation of energy because it has phase change.
okay. Mm.
So we consider heat source or heat sinks as this type of conservations. In salinity, basically salinity, I think in the ocean, salinity is treated as active tracer because it has some diffusion effect. There are processes called uh, salt fingering instability, in which due to the salt gradient the flows are changed. So I mean here we have not assumed any such effect of salinity or any other scalars. In oceans, if there is high saline water in one particular region and there is low saline water in some other region, though there are no temperature differences, water will flow from high saline region to low saline region, or I mean low saline water will enter the high saline water. So these exchanges will happen until the density becomes uniform. So that is the process of diffusion. So these are included in the equations for the determining the variables or the values of the variables. That's why these are important. Is it uh, sorry, is it fine?
Yeah, thank you.
Okay, so yes, so I think I had this much to present today. So I will just revise what we have covered. So we just talked a bit about the simple energy balance model with example of the change in the parameters, how it will affect the temperature, surface temperature of earth. And this is basically some small changes in the uh, parameters, how much change they will incur in the surface, and for large changes what we should do. These things we have discussed. We have gone to the definition of forcing and feedback and discussed some basic processes pertaining to the earth. And yeah, we have discussed the different processes, what would their effect be. For the assignment solving problem, we have covered the daisy world problem, but in a simpler version because we cannot solve the exact problem, and we have got an idea of how the calculations should go. And yeah, we have discussed the basic equations for general circulations. Of course, I mean that is the most complicated part for the modeling of earth system. So this should be in high priority, uh, because in simulations this take a lot of time and that consumes most of the computational resources. Now we have gone through the definition of stable and unstable equilibrium through a mathematical example and related that to the system of earth in a simpler way. Of course, determining the parameters is the most difficult thing because mathematics is there. Mathematics can always be explainable, and if mathematics exists, we get ideal type of solutions. But how to apply to the earth system is the biggest challenge for us. With this simple example, we have seen the stable and unstable equilibrium, and we talked a bit about the feedback mechanisms. What is the basic notion of the feedback, how they work, and finally we discussed about a problem for feedback. I think that's what we covered for today. Now, yeah, we will be ending the meeting, but again, for any questions, I am here.
Will these slides be uploaded or
Slides are uploaded.
okay?
you have got one link for the these recorded sessions. Have you got the link for the? I think you have got one Google Drive link in sorry, Google Sheet link. So in the sheet there is one link for YouTube, another link is for these slides. So that is my territory. So I just maintain the slides and the uh, I will also upload today's recorded session in the YouTube. Have you got the link for the first YouTube video?
Uh, okay, I haven't checked. I'll check it. I'll check.
Yes, so there is a folder, there is a link for an Excel sheet. There you will find both the what slides and the YouTube links. It will take some time to upload the slide and YouTube, but hopefully by today night you will get it.
Okay.
Okay, okay. If you have anything else, you can ask. Otherwise, we will end the meeting.
Everything's fine. Thank you.
Okay,
Thank you.
thank you. Thank you for joining and thank you for the interaction. Okay, I will